Sorry. Do you mind if I check something really fast? I think I forgot my book somewhere.
Oh, all right.
Sorry.
Okay, so now we're going to move on to chapter 5, where we're going to talk about population models. So basically what we were doing in chapter 4, we're going to do the same thing all over again, except now we're going to be thinking of the differential equations that we're dealing with as describing populations. In this chapter, there are 3 main models that we'll concern ourselves with. So, 3 main. There are other ways to model population, but these are the ones we're going to be looking at in this chapter. 3 main models to consider. So one is called the Malthus Model. That's the one that describes populations like P prime equals RP, right, which we've actually seen before. 2 is the so-called harvesting model, which is just a Malthus model with some non-zero constant change. So, or you can think of a Malthus model as a harvesting model where your H is 0 in either case. H we'll look at as a constant, and it can be either positive or negative. We're going to talk about what the differences are between those. 3, we're going to talk about the logistic model, which is P prime equals RP times 1 minus P over K. Right? And in this chapter, I think they sort of switch notations on us. They use big N instead of P. Either way, it doesn't matter. Unless in the question I specifically tell you a certain notation. I think in the handout, I used all N's. So let's not confuse ourselves here. So in this chapter, they switch to N instead of P. But we'll usually think of N as measuring some population. Right, so we're going to talk about what these means, and we're going to come at them from a different standpoint. We've actually seen 1 and 2 before, right? We saw this in chapter 2. And you notice that the harvesting model also worked for those money problems, right? When we had something growing with compound interest, compounded continuously, and we're actually depositing or adding money, right? So in this case, we're thinking of it in the population context where we either have individuals of the population being eliminated per unit time or they're being added per unit time. So that's how we're thinking of it, right? R will be the growth rate for the population. I wrote down what all the variables mean here, right? So R is just the growth rate, right? So if you're given a percentage to describe how fast this thing is growing, R will be the decimal value for that percentage. H is how something is changing per unit time, given that it was growing with the Malthus model before. And logistic is the model that's sort of supposed to be more real-worldly. Remember last time we spoke about one of the solutions to the differential equations, and we talked about, you know, how the population will rise, but only to so much, right? Which is what this K is signifying, the carrying capacity. It's sort of the optimal capacity for our population, right? And you will notice as N gets larger, you have 1 minus this guy, so you have 1 minus something that keeps getting bigger, so this is getting smaller. So this is telling you, as your population is growing, the growth rate is actually getting smaller, because the more people there are, the less resources there are. And so this model is trying to capture that, right? And so this is sort of the model that says, you know, eventually when your N reaches the carrying capacity, K, you get K over K, 1 minus 1 gives you 0, and the growing stops, right? But until then, the growth rate will decrease while the population is growing. And vice versa, if the population is decreasing, the growth rate will increase until it reaches its optimal state, right? So these two we've actually seen before, and we can actually solve them explicitly. We've done it. Separation of variables actually work for this. Yes?
So like, on the graph that we've been drawing, K would be the point of inflection before it stabilizes?
No. For this guy, the inflection point would actually be K over 2 all the time. But we're going to go over that. So these two here, we've actually done using separation of variables. Now we want to do qualitative methods for them. And this one, we will only do qualitative methods. We can do it using separation of variables, but the integrals that would involve, it's not in our syllabus, so I can't really show you the explicit way to do this, but we will be doing it qualitatively. Right? So these are the 3 models we're going to be talking about. So let's do our qualitative analysis. And so remember, qualitative analysis just wants to give us an idea of what's going to happen so we can make predictions. It will never really tell us anything super specific. I can tell the population is increasing, but I can't tell you at each point what the number of individuals are or something like that. I could tell you when a population is going extinct, but I might not know exactly when. This is just to give you an idea of what is going to happen. And if you want to investigate further, you can either, in some cases, solve it explicitly. In other cases, approximate it using Euler's method or something like that. So let's start with qualitative analysis. Let's look at the Malthus model. And let's illustrate with, let's assume that R is greater than 0, so this population is growing. And technically, R could be less than 0 if a population is decreasing. That is also possible. Okay? So let's look at n prime equals Rn. Now, when we want to do qualitative methods, what is the first step? You define the steady states and inflection points. Right? How do you find the steady states? Set the derivative equal to 0. So n prime equals Rn equals 0. This means that n equals 0 is the steady state. How do we get to the inflection point? Second derivative. So we find n double prime, which is going to be what? Just R. And what does that mean? We have no inflection points, right? Because inflection points happen when the second derivative is 0. I'm assuming R is not 0, it's bigger, this population is growing. So this is never 0, so there are no inflection points, since second derivative is not equal to 0 for any t. So this has no inflection points, but it does have, yes? You only have an inflection point if your second derivative is 0. Right? If you want to find an inflection point, you find where the second derivative is 0, and you have to look if the concavity switches on either side. That's how we do it. Here, the second derivative is r, which is just a positive number. Right? So no matter what, it's never going to be 0. Right? Our variables don't affect it. It's a constant. Right? R is a constant here. The growth rate is a constant. We're assuming it's constant for simplicity. Okay? So the second step would be to do what? Stability diagram. All right, so now we're going to graph n prime versus n. What would the graph of this look like? It's linear, it's a straight line. How does it look? It passes through 0. How does it pass through 0? R is positive.
Yeah, so it's going up.
So it's going up, right? R here functions as the slope for the line. It's like y equals mx plus b. So that's our guy. Okay, tell me about this steady state here. What happens? If I'm to the right, how do I? Arrow goes to the left over here. Arrow goes to the right. So this is actually an unstable steady state, right? So the population will head away from 0, which to us makes sense because it's growing, right? We have a growing population, right? So that's how that would happen. Third step is where we figure out concavity. Like I said, we usually skip this. It's sort of intuitive how we'll do it. The fourth step is to get to that solution diagram, right? The actual graph that describes this population. So now we want to graph n versus t, where 0 is our steady state. So suppose that the population starts with n0 equals some positive number, right? So it starts at n0, n0. Right? How will the population look?
Should be concave.
It will be concave up and
Going
heading
up.
away from 0. So that would be how this population is growing. It's just growing exponentially. And the reason why we have other models like the logistic model and things like that is because, as you can see, this is not really realistic, right? And you can only have a population doing this for a short period of time, right? Just growing without bound is not something that happens in reality. So that's why we have other models that try to make things more accurate. But for this simple model, this is how our population would grow, just grows exponentially, right? Notice if, and we're done there. Note, if we had R was less than 0, what would happen is the stability diagram would have been a line going like that, right? This would be that, this would be that. So this is a stable, steady state. And the smiley face there is sort of not good because that basically means the population is going to die. So it's very, the solution graph would end up being something like T. 0 is our steady state. If I start with any positive population, this says go towards 0. Right? Meaning I can tell from the picture of this thing that the population is going to go extinct at some point. I don't know exactly when, but it's going to happen if this model is actually somewhat correct, right? And that's what qualitative analysis gives us. It gives us an idea of what's happening in the future, even though we can't predict exactly from this method, right? But if I see that happening and I'm like, I don't want the population to die, I know something's got to change, I need to know how much time I have to fix the problem, I would do something else, do separation of variables or use Euler's method to sort of see, okay, you know, this population is going to be extinct in like 10 years if we don't do something. So we'll actually go through an example where we actually do this with a problem where I give you numbers for everything, but I just want you to see the overall process. What if I'm doing this for the harvesting model? How would things change? Let's do an illustration where, again, the population is growing, R is greater than 0, and let's assume H is greater than 0. Meaning I'm actually taking away something from the population. So this is happening where something like, you know, a population is growing, but a certain number of members are dying, like a predictable number of members are dying every year or every so often, right? So you can have a population of an endangered species, and they're endangered because people are hunting a certain number of them, right? You could use this model. You can say, yeah, this is how they're growing normally, but we're hunting some of them, and we kill an average of this many per year. This is sort of the model you use. That's called harvesting, when you try to, you harvest individuals from the population. Okay? So in this case, step one would be, you know, find steady states and inflection points. For steady states, remember you said n prime equals Rn minus h equals 0, which would mean your n is h over r, right? That would be where your steady state is. What about inflection points? In this case, the second derivative would again be r, so there are, in this case, again, no inflection points. How would the stability diagram look? It's like y equals mx plus b, right? Your b is negative because your h is positive, and you're minusing a positive number. The slope is positive. What would this picture look like?
A line going up, passing through the negative side of the y.
Yeah. Right? So here, it's passing through the negative side of the y-axis. In fact, it's passing through minus h. What does it pass through here? H over r, because that's what we solve for the steady states. Now do the analysis on the steady state. On this side, how do you draw the arrow? It goes left because the graph is underneath the horizontal. On this side, we draw it right because the graph is above the horizontal. This is an unstable steady state. And how does that actually change things? So what does the solution graph here look like? Now we have the steady state is at h over r. There are no inflections to worry about. And so what do we know? If our initial population is above here and 0, what's going to happen?
Concave. All the way up.
And increasing, right? Because our arrow says go away from the steady states. It's an unstable steady state. So if I'm above, I will grow, right? If I happen to start below this steady state though, we will die, right? So then, for this population, what you'd realize is, well, depending on the H and the R and all that, if the population starts out with a certain amount of number, you'll never actually kill everyone in the population, even though you're hunting them, right? But if the population was too low in the beginning, that's too bad, because with hunting this number of things, they'll actually all die out, right? So this model will sort of tell you to keep things in check. Watch how many of these individuals you're eliminating per unit time, because it actually matters. Measure how many there are right now, and then make sure you keep your H over R in check. Right? You can't make that H, too large until it passes the population. That would be bad, right? You might make your H smaller so that it goes below the initial population, right? You can tell what you have to do to fix a situation. So you can say, oh, H is too big, we're hunting too many, because their initial is down here. So you make H smaller, put it down, and you end up with the population surviving. So. Let's look at the logistic model. We're going to assume R is greater than 0 and K is greater than 0, which is always the case you're going to be given. So pretty much a logistic model will look like this no matter what the numbers are. You're just going to be changing the numbers. The last two, though, can have some variations. That is, we are looking at n prime equals Rn. Let's examine this guy. So that's steady states and inflection points. For steady states, we set the derivative What are the solutions here?
N equals 0 and then is equal to 1 over k.
N equals 0 or n equals
1 over k. K,
N
1 equals
K.
k.
right? So remember, when you have two things multiplying giving you 0, you set one or the other equal to 0. So either Rn equals 0, which means n equals 0, or 1 minus n over k equals 0, which means n equals k. So we have two steady states in this situation. What about inflection points? Well, I would need to take the second derivative. So n prime is equal to, you can take it with the product rule, but I probably want to multiply out Rn minus Rn squared over k. Right? And then I can find the second derivative, which here, just take the derivative of that, I get r, take the derivative of that, I get 2Rn over k. And now I want to set that equal to 0. And what's going to happen? If I have r minus 2Rn over k equals 0, I can multiply both sides by k. Multiply by k, right, just to get rid of the fraction. I can also divide both sides by r. R is greater than 0. I'm not dividing by 0. And then I can just bring the n over this side and divide by 2. And I would get n equals k over 2. So add 2n, then divide by 2. And so this is going to be the inflection point. So you're pretty much always going to be given this situation, and this will always be what it works out. Whatever I tell you the k is, k over 2 is going to be the inflection point. And 0 and k will always be the steady states, right, for the logistic model. So it's just something that you can just know right away. Let's get to the stability graph. What would that look like? What does the stability graph look like here? The graph of this guy. It's a parabola, right? It's an n squared graph, so it's a parabola. Like a smiley face parabola? No, because the squared term is negative, so it's an upside down parabola. This is the steady state, which is at 0. This is the steady state, which is at k. The inflection point, remember, happens at the maximum. This happens at k over 2. That is your inflection point. These guys are steady states. Analyze this steady state. To the left, the graph is underneath, so we draw an arrow to the left. To the right, graph's above, you draw an arrow to the right. This ends up being an unstable steady state. Here, graph is above, arrow to the right. Over here, the graph is below, so I draw an arrow to the left. The two arrows going head to head, that is a stable steady state. So this is sort of telling you your population will tend towards whatever this k is, whatever the carrying capacity is, that is the optimal place for the population to be. If you're below that, you will go there, and if you're above that, the population will decrease and go there, right? You'll either increase towards it or decrease towards it, because that's where the population stabilizes at its carrying capacity. Again, 3D state for solution graph. Our steady states are 0, k, you have an inflection point at k over 2, half of whatever the k value is. So we're thinking of population, so the negatives don't matter, they don't make sense for us. But what if we start with the initial population here? Is it increasing or decreasing? Increase, right? Once it's above 0, it will go towards k. So we know we're going up. What's the concavity here? Concave up like a smiley face, because I want to switch the concave down to settle at this steady state. So that would be, if your population starts below k over 2, that's what it's going to look like. The fastest growth rate happens at this point. Right? That's where the slope is the steepest. What if I start slightly above k over 2 but less than k? Right? Is that my initial? What would happen?
Concave down.
Increasing concave down, because I want to be able to settle at that steady state. What if my population was higher than the k, like in 0?
Decreasing concave up.
Decreasing concave up. Okay. So now, k will always be 0. You can't have a negative carrying capacity, obviously. And your R can be less than 0, but I've never seen that situation show up on a final. So you can pretty much see that this will pretty much always be the situation. You're going to be filling in numbers here, and literally nothing would change. Like a logistic model, you can literally just memorize this method. Like, this is what it's going to be, right? You're just going to be filling in numbers here. Whatever they tell you R is, K is, you just put it here. You know, the second step will look like that. The fourth step will look like this, and they'll just tell you one of these places to start, but this is what it will look like. More than likely, they'll tell you somewhere here, because they want to see if you know how the concavity works, you know, so things like that. But this is the logistic model, right? And it's sort of the model that tells us, no, populations have a level that they will stabilize at. You know, it's not like they grow forever. You know. And in this particular population, as long as it's growing, it will never be extinct. It will always go to this point. There is a model that has harvesting for the logistic, and that one could possibly go extinct, but we don't cover that one. I think it's actually called the real world model. So basically those are the models that we have in this chapter. And now we are going to do some specific examples, which are written on the handout. So I put them on the handout because I don't want to bother writing them, so just make a note. Problems on class handout. Let's do problem 1. Now, a population model will definitely be on the final, but it's highly unlikely it will just be a Malthus model. You'll either get, I'm pretty sure a logistic is coming on, and if one of the other models come on, it will be the harvesting model, because the other one's just too easy. But let's actually do problem 1. Okay. And I sort of did the wording that some of your homework problems have, so you can sort of see how this works. The Jhevonian population has a birth rate of 31.4 per thousand per year and a death rate of 2.72 per thousand per year. Assume the population grows at a rate proportional to its current size and it is allowed to grow in peace. So basically, if I make n the number of Jhevonians at time t, it grows at a rate proportional to its current size and it grows in peace, right? No one's killing anybody, right? This is the model for this population, right? N prime equals Rn, right? So that's what, when it says growing proportional to its size. What it told you before about the birth rate and death rate is actually telling you how to figure out what R is. R is basically going to be birth rate minus death rate. Right, so figure out how many are being born versus how many are dying, and that's telling you how the population is changing. Right? It's possible for R to be negative, but in this case it's positive because they told us, right? And they said 31.4 per thousand per year, so the birth rate would be 31.4 per 1,000. So you divide by 1,000 minus 2.72 per 1,000. So this would be 0.0314 minus 0.00272. And what's that?
0.02868.
0.02868. Right? So that's how you'd find this, the growth rate for this population, right? So in the case where you're given birth rate and death rate, you just subtract the death rate from the birth rate, and that tells you how the population is growing. So in other words, here, n prime is equal to 0.02868 n. Now we're asked to analyze this qualitatively, right? Meaning they want us to use pictures. So while this is separable and we can solve it using separable techniques, we're specifically asked here to use qualitative methods. So let's start with A. Step 1 in our analysis consists of what? Steady states and inflections. So steady states n prime equals 0.02868 n equals 0, which means that n equals 0. That's the steady state. Inflection point, I said n double prime, which is equal to 0.02868 equals 0, never 0, obviously. So no inflections. What's the second step in the analysis? Stability graph. So I want to graph n prime versus n. What does the graph look like here?
Straight line,
Straight line
positive.
through the origin, positive slope. The slope is actually 0.02868. And that's the steady state 0. Is our steady state. Look to the right and to the left of 0. The graph is underneath the horizontal over here, so we draw an arrow to the left. It's above the horizontal over here, we draw an arrow to the right. It's an unstable steady state. We're running away from the steady state in either situation. we can skip because we know how to use our intuition. Finally, we want to get to the solution graph. How will this population behave in the long run? N versus t. We care about negative time. 0 is the steady state. Okay. So it says use qualitative methods to analyze a population if it starts with 60221 individuals. So I start here. That's created of 60221 individuals in this population. What's going to happen to them? They will increase, concave up. The population will grow exponentially. So our analysis of this situation is the Jhevonian population will grow and prosper forever. Okay, all right. So now in part B, we're asked to find an equation that describes a population. So we've done the qualitative methods, we sort of see what's going to happen, but can you tell me a specific equation for this? What is the actual curve that we just drew there? Yeah, how do I find it, the exact one?
Separation of variables.
Separation of variables. We have n prime is equal to 0.02868. Was that it? Yes. N, we're given that n0 is 60221. So I can use separation of variables to get to an exact one. This means I have dn over n is equal to 0.02868 t. Integrate both sides. Here I get ln n equal to 0.02868 t plus a constant. This means my n is equal to c e to the point 0.02868 t. And then 0 is equal to 60221, which means that 60221 is equal to c e to the 0, which means your c is 60221. This means the equation for this population is 60221 e to the point 0.02868 t. And at this point, going through a separation of variables problem should be like, yeah, this is the next step. You get bored while doing it, hopefully. That's what should be happening by now. So that's part B. Part C. What will be the size of the population after 7 years? Plug in 7, right? Size after 7 years equals n of 7. T was measured in years. So this is just 60221 e to the point 028 equals 60221 e to the point 02868 times 7. Give me an estimate on that. 73,610. So with this sort of growth, after 7 years, there will be 73,610 Jhevonians. The problem requires the use of what model? What model did we use here for this problem?
Malthus.
It's the Malthus model, so you can fill that in that we use the Malthus model. Hopefully you realize why we use the Malthus model. It's because they were growing in peace. No one was removing the population, you didn't have all these people coming in and taking over our resources. Okay. Any questions on what we just did? It's really chapter 4 all over again. We're just applying it to populations now. But if there's anything still unclear, now's the time to ask. If not, we can move on to problem 2. Okay, no more peace. In the 7th year, an evil race of dark elves waged war with the Jhevonians. 3,000 Jhevonians per year fall in battle. If things continue this way, will the Jhevonians survive? If not, when will they be annihilated? What model are we going to use here? Harvesting. So here we're going to use that n prime is equal to Rn minus h. Some individuals are being eliminated from this population at some predictable constant rate. Normally the Jhevonians would grow at a rate of 0.02868, but now we're eliminating 3,000 per year. So then I put minus 3,000. The rate is being decreased by that many. Let's start our analysis. What's our first step? Qualitative analysis of this situation. We need steady states and inflection points.
Can I ask you a question about the harvesting number?
Yeah.
So if we were adding,
You put a plus here.
It'd be a plus. Okay, so wouldn't it then be like the normal formula shouldn't be a positive because like it shouldn't be a negative h, it should be a plus h because h would be negative?
Well, it depends on how you're thinking about it.
Okay.
I mean, it could work out with a plus, but when you plug in the numbers and you look at it with the numbers, you should have a negative if you're decreasing and a positive if you're increasing. You could actually memorize the formula in either way, but it's because it's harvesting, it's usually assumed that you're taking away something. It's just like, it was just a natural way to think about it. But by the time you get here, the sign should tell you what's happening. Here we're subtracting 3,000. Okay, so steady states mean I need to set the derivative equals 0. This means that n equals what? It's going to be 3,000 over 0.02868, which is roughly what? 104,602. 0.5. Let's just round up. Let's make that. Let's keep things in whole numbers because we're talking about population. Okay. So that will be steady states. Inflection point, second derivative is equal to 0.02868, which is not 0, so we know we have no inflections. We're going to do the stability graph. This looks like y equals mx plus b. Your slope is positive. Your y-intercept, the vertical intercept is negative. So this is just a straight line with positive slope, but it's actually going through here. So this is at minus 3,000. This is at 104,603. And we can do the analysis at this point. To the left, we're underneath, decreasing to the right. Unstable steady state. did that because we're professionals here with the solution graph. Or maybe I'm just unprofessional. I think all the other classes, the professors are forcing them to actually do that. All right, solution graph. What does it look like? So the steady state to be 104, 603. This is steady state. All right, so what is the initial point here? 17,610. We know after 7 years that's their initial, right? The initial is 73,610, right? This is the number after 7 years. All right, so here was this population growing in peace, but 7 years after they started growing, boom, war happens and this new situation takes place. What happens? We're below the steady state. This says we go towards 0 and boom. If this situation keeps up, the Jhevonians will die out. And I, for one, think that that's a huge tragedy. We need more of them. No, it was an unprovoked attack. You don't even understand. We were growing in peace. What the hell? Okay. So if this keeps up, will be annihilated. So the question was, if things continue this way, will they survive? The answer is no, they will not survive. And if not, when will they be annihilated? Right? So this can tell me that it's going to happen, right? But when will it happen? How do I figure that out? If I want to be specific and figure out what time is this? You have to actually find the equation for the thing and say equal to 0. So this was part A, I believe. Well, it's not really labeled part A and B. So we have n prime, well, let's call it dn dt equals 0.02868 n minus 3,000, where n of 0 equals 736. This means factor out this guy, and this was 104,603. And divide by that, dn integrate both sides. Notice, by the way, when we factor this guy out, we end up with a steady state. ends up being CE to the 0.02868T plus 104,603. And then 0 equals 73610. This implies 73610 is equal to CE to the 0 plus 104,603. This means that C is equal to 73610 minus 104,603, and that's what? $30,900. Huh?
993.
So our population can be modeled by 30993 e to the 0.02868 t plus 104,603. So that's the actual equation that tells us how our population is behaving. For extinction, our n equals 0. This means 0 should be equal to minus 309. And how do we solve this?
Subtract 164. Subtract 100,000.
Subtract the 104. Then what would you do?
Divided by negative.
Divide by this guy. And what's this? 104. And divide by that. 3.3738.
Actually 3.3750.
3.375 is equal to e to the 0.02868t. How do we get to the t? Log both sides. Kills e on this side. So your t is going to be equal to ln of 3.375 over 0.02868, which is roughly
42.
42. It's 42.
42.41.
The answer to life, the universe, and everything. That's a coincidence, isn't it? So they can only stand this war for 42 years. I mean, I think that gives us time to change something. Develop new weapons and warships. So A and B, we did the qualitative analysis and then we actually solved things explicitly. For part 3 though, we actually can't do that. Because there's no secret here. We're using the logistic model. I told you the carrying capacity and all that. So we can't solve it explicitly. We can only do qualitative analysis, right? So pretend the war never happened. Just making up stories. All right. So the Jhevonian population, after some research, we found out that they have a carrying capacity of 200,000. If the initial population is 60221, reanalyze the population using qualitative methods. This problem requires the use of the logistic model. So let's do that. So in this case, n prime is equal to Rn 1 minus n over k, which means in our situation here, n prime is equal to the r was 0.02868. 1 minus n over 200,000. Step 1, steady states and inflection points. Steady states is going to be what? 0 and k. Inflection points is going to be n equals k over 2 equals 100,000. And you can go through the calculations, but as I was showing you, it'll all be the same. You really have no choice about how this thing's going to work out. Right? So for a logistic model, the steady states are always 0 and the carrying capacity, and the inflection point is always half the carrying capacity. Once your R and your K are positive, which in this case they are, that's what's going to happen. So you can do less thinking. If your R is negative though, things will actually start to change, so you have to be more careful. So actually watch out for that. This might be the year the person writing the final decides, you know what, let's do a decreasing population with logistics. Could happen. Okay, so be careful of that. Once your R is positive, it's pretty much standard stuff that's going to be happening. 2. Stability graph. Again, pretty standard. It's going to be an inverted parabola. Say it's going to be 0 and k, which in this case is 200,000. The inflection point happens halfway there. That's 100,000. This will always be an unstable steady state. This will always be a stable steady state. I mean, you write all this down, but it's really just like going through the motions. We skip that step unless you still have trouble with the intuition. You just go through that table of signs that I showed you. And 4, you get to the solution. Is a steady state. The other steady state is 200,000. Inflection point is 100,000. Okay, what does our solution look like here? 60,221 individuals, meaning we start where? Below this guy. So we start with 60221.
Okay, well, increasing is 1,000, where then it's increasing.
So that's what will happen to the population. Right? They'll keep growing until they hit 200,000. They'll start to grow at an increasing rate here. Right? It's a community and all that, everyone starts helping each other out. But then they hit this peak where now, oh, there are too many people, resources are getting scarce, and they start to grow, but they grow slower until they reach the optimum point of the population. And that's the end of chapter 5. That everything you learn from chapter 5 by reading it is this 3 population models. Any questions? I was supposed to take questions on the homework. I think I forgot that. Anyway, for now, homework is due for chapter 5. I guess you could keep the chapter 4 homework until you ask me questions about it next time. But let me be specific as to what the homework is. Hold on. I was supposed to take questions on the homework. I think I forgot that. Anyway, for now, homework is due for chapter 5. I guess you could keep the chapter 4 homework until you ask me questions about it next time. But let me be specific as to what the homework is. Hold on. Yeah, 7 and 8. Homework 7 and 8 are due next class. So I'll take questions on homeworks 6, 7, and 8 since I didn't get homework questions on homework. Okay. So that's chapter 5, and I guess if there are no questions, we can go.